Welcome to this session. This is a deep dive session on running Kubernetes on the vSphere hypervisor. My name is Steve Wong. I'm an engineer with VMware based in Los Angeles, California. I've been working on Kubernetes since 2015. I got started working on storage, but recently I've been working on vSphere related things. And I'll let my partner introduce himself.
Thanks, Steve. My name is Hui. I'm the software engineer at VMware. I've started working on Kubernetes since beginning early this year, and I'm the active contributor to upstream Kubernetes, like device plugin.
Oh, I think it's not on.
Hello? So I also contributed to cloud provider vSphere and cluster API vSphere.
And our GitHub IDs are there on the slide if you want to get in touch with us. By the way, we have uploaded this presentation deck already to the Sked site, so you should be able to get access to all of these slides. And in many spots, there are hyperlinks for other information that are live in that uploaded presentation. I'm going to skip the abstract because I presume you read it already when you came here, but I put it in the deck just so that if you find it later, you'll know what this presentation is about without going through the whole deck. This is what we're going to cover today. So we're going to cover Kubernetes default scheduling, kind of the generic mechanism. Just so you know, scheduling is the process where you take a pod that's ready to run or desired to run and choose what worker node it runs on. So that's scheduling, and we're going to cover what you get by default. Then with the vSphere cloud provider, it turns out that you have some additional options that are not necessarily there on every cloud provider that can help you improve scheduling, and I'll go into why you might want to use those. Next, I'm going to hand it back to my partner, and he's going to cover NUMA, non-uniform memory architecture. Finally, we'll move into the default resource management. Resource management is the concept of these worker nodes have finite amounts of CPU cores and memory, and the pods have appetites for this. And you'd nominally like to have these things be scheduled efficiently, yet not have things like noisy neighbor problems or pods starved for resources or even being killed when they go over limits. I'm not sure we're going to have time for these because at 35 minutes I put a bunch of slides in this deck, so we may or may not get to these. I'm going to respect the time period, but I did put them in the published deck, so if those of are interested, if we don't get to those, you can look at the deck and get the information anyway. So Kubernetes scheduler, what does a scheduler do? Well, as the pods are created, they're actually put into a queue. And this queue, by default, they might be ordered first come, first serve, but there are mechanisms with Kubernetes where you can assign priorities such that a pod gets enqueued and jumps ahead in line. And they get into that queue. The scheduler continuously pulls pods out of that queue, looks at the requirements. So you really should have a statement on your pod YAML that declares what the resource requirements of that pod are. And this helps the Kubernetes scheduler make a better decision on where to place that. Depending on how you have Kubernetes deployed, you may be able to leave that out, but it's generally a bad idea, and because you don't get predictable behavior on how those get deployed. So how does this placement decision work when that control loop decides which worker node it's going to be assigned to? First of all, it filters out all the impossible worker nodes. You can have things, declarations that might use labels on these pods saying, I can't run on this pod. You might have a resource requirement statement that says, I need 100 gigs of RAM, and any of the worker nodes that can't fulfill that requirement are impossible worker nodes, so we throw those out. And it actually, if you have real specialized requirements, there are these filters are called predicates, and this is extensible. So in theory, you can write your own to supplement what's in Kubernetes or even replace it. Finally, once we've eliminated the impossible nodes, we rank, let's just say that we had 10 nodes. 2 of them are incapable of running this workload, but 8 remain. There's an attempt made to rank the remainder to choose what might be preferred here. And once again, this ranking is delivered by plugin modules, and there's a default collection of these built into Kubernetes, but it is possible to supplement that with custom written code that you would do yourself. I'll give you one other clue that if you have a huge cluster, I forget what the breakdown is, but I think it's at least hundreds of nodes. Kubernetes doesn't actually go through the entire list. It will just maybe take a subset of the non-impossible nodes, filter those, and in the interest of latency, rather than going through thousands of nodes for an evaluation, it will look at a subset, and if you get a high rank in this subset of it will go ahead and schedule it somewhere. And I believe that's configurable so that if you wanted to really force it to look at all of them, you could. But I'm telling you, the default is that at a certain cluster size, it actually just grabs a portion of the eligible nodes and ranks those. So the steps are the pod's created, it's enqueued, evaluated, the nodes are evaluated, filtered, ranked, and then that pod is actually, the X's are the impossible ones, this is the ranking, and it would go to the preferred node, which had a 1 on it. So what can you do to modify the scheduler? There are node selectors that are based on labels. There are affinities, so this is used to say that I want my pod to be scheduled on the same node as another one or never scheduled on the same. This list of elements that can influence this are zones, taints, tolerations, and there's a number of these admission controllers that can affect that placement too. So why use zones? Well, Kubernetes, if you label your worker nodes with zone labels, you would do this to indicate failure domains within your data center so that you can use this to help the Kubernetes scheduler automatically spread out horizontally scalable services across failure domains. And that's why you would want to use these zone labels. If you're on vSphere, these zone labels can be applied to ESX hosts. Those are hypervisor hosts if you don't know that much about vSphere. You can also put these labels on data centers and DRS clusters. So when you do this, the scheduler will use these to properly spread this out, but I'll caution you that this falls into the category of what's called a priority, and they have another category called a predicate, so that if it looks like you wanted 3 nodes running, but there's insufficient zones, you only had 2, it's rather than not schedule your workload at all, it's going to put 2 duplicates in the same zone. So it's a best effort thing rather than a guarantee. Next, we'll move on to zones. Zones is used for spreading workloads. NUMA is an interesting concept, and I'll let Hui cover it.
Thank you. First, I want to ask a question. How many of you heard about the NUMA before? Okay, 4 of you, and that's good. So NUMA stands for non-unified memory access. The picture here showed is NUMA architecture. We have 2 CPU cores here, and
actually sockets, right? Or
Yeah.
Right. Okay.
But we can also call it core.
Okay.
On the left side, you have memory. You have 12 memory DIMMs with 6 channels, and on the right side, it's the same. The design in this way, if the CPU 0 want to access the memory on the left side, it has latency here for this one. In the example, it's say 75 nanoseconds. And since this is a NUMA architect CPU, both CPU can access all the memory, both on the left side and the right side. But there's a penalty. If CPU 0 want to access the memory on the right side, it actually have to go through the interconnect, which is which actually has overhead. So the latency will become 130 nanoseconds. And also the bandwidth will be limited by this interconnect. So the problem is, if you are run application and if you care about the performance, then there's about can be 80% difference in terms of latency and also the bandwidth. So that's what we are trying to discuss here. If your application performance sensitive and you are running on the Kubernetes, and how can you make sure first you want to improve the performance, second actually you want to make your application performance predictable, means maybe it's not the most optimal, but you want it always in a predictable way, means it's flat. It's like a fluctuating, and actually consistency is the key, and it's more important than you have optimal performance in 1 second and you have bad performance later. So I covered a little bit why we care about NUMA. If you care about performance, then you have to care about NUMA. Especially in the old days, we have UMA, means Unified Memory Access Architecture. Now, modern data centers and modern servers, especially for the enterprise, for the servers, they're mostly NUMA, means you have more than one sockets, and you have non-unified memory access. I consider there are two types of situations that your application are not accessing your local memory, means you don't have the most optimal performance. One situation is your application running on the CPU 0 here, and the memory in this CPU already get allocated. So when you start to request memory, you are getting memory from the right side. So in this situation, you may get some memory on your local, and you also get some memory from your remote. Then you have a mixed set of memory, and your performance is suffered a little bit. Another situation is for some database servers, it's try to allocate all the memory in the server. So if you are running on a server with multiple NUMA, multiple sockets, then it's inevitably getting all the memory, means it has a lot of remote memory allocated also. If you want to avoid that situation, if you want a better performance, you want to avoid this situation. So now the question is, how can we avoid those issues? So
there are two general ways or methods. One is I talked a little bit for performance. The consistency is very key. So you can tolerate its average performance, but it's very consistent. It's linear and it's flat. One way to do it, if you are running on the Linux VM, you can use, or Linux machine, you can use a NUMA control command to interleave the memory. Means you are getting memory from all your memory node, and you get an average performance, but you get it very consistent memory access because you're accessing all the memory node equally.
You'll take half of your memory from the good fast side and half from the slow side, always.
So this is just one way, but I'm going to show you if you are running on the hypervisor like the vSphere environment, we can do better because we can, for Kubernetes, we can probably properly size the node size within the NUMA boundary. Means I'll go back to the picture here. So I'll create a virtual machine that the number of virtual CPU is equal to the number of physical CPU in one socket. For example, if the socket on the left side is actually 8 physical CPU, then I create an 8 virtual CPU virtual machine. And on the hypervisor, we have something called the NUMA scheduler. So when the VM gets scheduled and you are requesting memory, actually it's going to get all the memory from these on the left side. Means they are mostly from the local memory. And if your workload starts to accessing more memory and you actually get more remote memory, our scheduler actually will start to migrate you. Means it's not affecting your application, but it's move you to a new NUMA node so that you still get most of the memory from local. So the key here is the NUMA scheduler will do the intelligent scheduling and make sure your performance is still consistent and also better. So the requirements for the developer is when you create this node on the hypervisor environment, you have to pay attention how to size your node. How much memory, how much virtual CPU and other devices. And the guideline we can give is on our vSphere environment. The first we want to give is, if possible, just size your node within the NUMA boundary. Means your server have in one NUMA node how many physical CPU costs and how much memory. Then you create your Kubernetes node, the virtual machine, accordingly. But there are cases that your application do require bigger size node. So our suggestion just limits how many number of NUMA nodes you may require. For example, if you can fit into 2, then don't go up to 3. Another one is the number of vCPU. Don't give an odd number of vCPUs. This is just because in the reality, all the Intel AMD servers, the number of cores in a physical CPUs in one NUMA node usually is an even number, is 8 12, and it's never be 7 or 5. So your VN's vCPU number should also be something like 8, so that we can place this VN in an optimized fashion. Otherwise, we will face some bin packing problem. We have an 8-core CPU physically, and you create a 7 vCPU VM, and we place there, then we only have one core left, and it's hard to put another VM, schedule another VM into it. And the last one is never create a VM that you have a number of vCPU that larger than the physical CPU the host has. That's actually obvious. You actually don't want to do that. And the benefits of doing this is actually to achieve consistent, predictable performance on the Kubernetes, and this is what with the hypervisor environments, our hypervisor scheduler, NUMA scheduler, can help you immediately now. And in the near future, or in the future, the Kubernetes community has also started to work on this problem or start to tackle this problem. There's a discussion about NUMA proposal and discussion around the NUMA manager in the upstream community. And the community want to address this issue in all different kind of environment, not only the hypervisor environments. And if you are interested, please join the discussion, this link. And with that, I'll hand over to Steve to talk about the resource management.
Okay, thanks, Wei. So on to the next topic, resource management. Let me start with explaining how it works. So every time you declare a pod and this gets dispatched, these resources, and resources are things like CPU cores, memory, they're metered on a per container basis. So inside of a pod, you could have multiple containers, but you specify the resource requirements on a per container basis if you happen to have, say, a 3-container pod. These resource requirement statements are broken up into 2 parts. One is a specification of requests, and this is a declaration that, look, I need 1 gigabyte of RAM minimum, and this is the minimum the container is guaranteed to get. And if that just isn't available, the pod's just not going to start. You can, in addition to the request, you can ask for a limit, and this causes Kubernetes to impose a limit to prevent noisy neighbor problems. For example, let's say I had a memory leak in the application running that container, and it proceeds over time to gobble up more and more memory without limit. Specifying a limit on that container will cause Kubernetes to monitor consumption and potentially even terminate that pod should the limit get exceeded. These requests and limits by default are unmanaged, but a mechanism exists in the cloud provider for the admin to supply defaults so that if somebody puts out a container, a pod spec that doesn't specify these, it can automatically act as if these defaults were specified in the YAML for each of the containers in this pod. There's another mechanism for keeping control of these resources at the namespace level. This would typically be used to allow an administrator to impose a quota per department or per working group within the company. So maybe you've got an accounting department, a dev department, and a test department, all sharing the same collection of these worker nodes. An administrator can go assign each of these departments to a namespace and impose some governance so that the developers can't hog everything, leaving nothing left for production, for example. So these resource quotas are a very useful tool for specifying requests and limits. There's even a mechanism to take certain types of resource objects and impose these, like limiting the number of config maps, persistent volume claims, secret services, and it really is a mechanism to prevent people from going out there and hogging everything and preventing others from getting fair access to these types of resources. When you specify these, when you're specifying requests and limits for CPUs, this happens to be in units of millicores, which are 1/1000th of a core. Memory is specified in these megabytes, and you can see the formula there. I will caution you that on Kubernetes, these cores potentially, if you have non-uniform hardware, don't take that into account. So if I have some 5-year-old servers that have 2 gigahertz CPU cores, and then I bought some new ones a month ago that are twice the speed, the Kubernetes scheduling process and resource management doesn't really take that into account. Now, when you're on a hypervisor like vSphere, you can potentially adapt for some of those sorts of things in the underlay in the hypervisor to get more predictable behavior. But the default Kubernetes, when you run it on bare metal, really it just blatantly assumes that every core in the entire cluster runs at the same speed for its behavior. So the way these resources work is actually a nested series of goals, isolating workloads, giving high priority workloads first claim on the share, imposing fairness, and scheduling with efficiency to maximize the consumption of the resources physically available in the underlying hardware. The built-in resource management in Kubernetes enforces these limits at the worker node level. So there's code running at the worker nodes that are monitoring what the specified limits are and what's allowed and not. When you run short of CPU, what happens is if you violate a limit, you actually just get throttling, where the time slicing of the periods with which you have access to the CPU core are cut back. Memory, on the other hand, is incompressible. So if you trigger a violation there of a limit, you get the death penalty. Your container can be terminated. This enforcement is not instantaneous, and these are configurable on Kubernetes. So you can, if you choose and as an administrator, you can give them a grace period where they might be able to go over the limit for a very short amount of time and escape the death penalty. This is what goes on there. But when you're initially scheduling that, if a node doesn't have enough to support a resource request, it simply will not be put on that node. After scheduling, pods aren't affected by this quota. So resource management enforcement is actually working in a hierarchy where it operates on Kubernetes. Some of this gets passed down to the container runtime. It might happen to be, your Docker runtime or some other container runtime. That in turn can pass through down to the Linux operating system and kernel itself. And if you're running on a hypervisor, which is optional, and you could run it on bare metal, but if you run on a hypervisor, there's an opportunity there to have the hypervisor itself engage in some resource governance for you. So the Kubernetes control plane is where you declare and manage desired policy. The enforcement passes down through the pod to the container runtime to the OS. Down at the OS, it's C groups that are used to map pod CPU and memory resources to whatever enforcement and monitoring takes place. And those are the C groups drivers that are involved. Okay, I'm going to have to speed this up, so I'm not going to read this, but look at the picture. We're nearing the limit. So it turns out that if you're on a hypervisor and that hypervisor is vSphere, there's an existing mechanism called DRS, Distributed Resource Scheduler, that can actually load balance VMs on a hypervisor cluster, and you can put multiple tenants on these. In this case, different tenants are in different colors. We've got master nodes, production worker nodes, over here, test worker nodes, and you can actually use the vSphere DRS to prioritize resource allocations based on these departments and have this enforced down at the underlay, the hypervisor level. So we've got 5 minutes left. I'll open it up to questions at this point. I'll tell you that when you go download the deck, some of those other things that were in the agenda are in slides after that thank you slide, and it's explaining how you go configure vSphere, in either the UI or you could use the CLI to take advantage of these features. But download the deck later. There's also a feature called high availability where you can potentially use the underlay hypervisor to automatically migrate VMs from one cluster node to the other, and for some critical applications that might be of great interest to you. So at this point, does anybody have any questions? Even if it isn't on what we talked about, if it relates to Kubernetes and vSphere or even Kubernetes, we'd be happy to take them if there was something we rushed through. 35 minutes is a little short for this topic, unfortunately, but sure. Can you give them the mic?
vSphere and physical volumes, physical volume claims.
Persistent volume claims, probably, right?
Yeah.
So what's the question, or you want me to just summarize them?
Well, I have a cluster coming up that's going to go on to vSphere. I'm doing this right now in AWS.
Here, give them the mic.
I'm doing this right now in AWS with EBS.
Okay.
We're moving to a dedicated data center with vSphere.
Okay.
What's a good way to do it with vSphere?
You definitely want to run the vSphere cloud provider, which right now, these cloud providers, that's an in-tree cloud provider, meaning it's already built into Kubernetes. But you do have to configure it to turn it on. So it's a config parameter when you start up your Kubernetes cluster. Some distros, if you're getting a distribution, might do this for you so that whether you know it or not, the cloud provider is being engaged. But there is documentation explaining how to do it manually if you just take the open source Kubernetes, don't take anybody's distro and run it. And what will happen there is that for persistent volumes, you're just free to use whatever storage is. If it works in the vSphere hypervisor, it will work for you. So if this is a greenfield application with a modern vSphere, you might well be using vSAN. If you're in a legacy data center, you might have some external SAN arrays from any number of vendors. There's essentially everybody in the IT industry, I think, has drivers to support storage through vSphere. And if it works for VMs, it should work for your containers. What will happen is If you only have one type of storage, you should go there and make that your default storage class. Just like on Amazon, EBS volumes are your default storage class. And if you declare a volume, that's going to be what you get. Now, with vSphere, it's possible that you'd have multiple tiers of storage, maybe some super fast stuff that is very high-end SSDs, and then maybe some bulk storage that's cheap, but you have it, and you can define, an administrator can deploy multiple storage classes. There still would be a default, but you could get potentially great advantage of having maybe the cheap storage used for log files and the high performance stuff used for your database caches. And what you would do there is define these storage classes as an admin and let the developers specify in Kubernetes, you might know this already on Amazon, it's the same way AWS would work, where you have persistent volume claims that would specify a storage class. If they leave it out, they get the default, but if they specify it, it gets mapped to these. My goal, if you're moving from AWS, this implies to me maybe you're running multi-cloud, where some on-prem, some in the cloud. You should make those storage class labels be labels affiliated with desired outcomes. So never label them with the name of the physical vendor. You might want to label one fast, expensive, the other one cheap, so that people, okay. And that way, people labeling by desired outcomes, it just works wherever you're running, in a cloud, on-prem. And the other advantage of that is, interestingly enough, it works over time. So, you know, if you go back in a time machine 5 or 10 years ago, fast might have been 15,000 RPM SAS drives, and slow would be, I don't know, SATA drives. But if your developers broke the database servers into one, log files get slow, indexes get fast, that still totally works, and you never had to go change anything, and it just does the right thing. So that's my takeaway for persistent volumes. And you can make vSphere, arguably you can get more classes of storage potentially on vSphere than you could in Amazon, because they offer a finite number. And it is also, when you get to storage, you should probably also use that zones feature potentially that I clued you in on. And that can get complex because you might want to conceivably map storage affiliated with what your failure domains are in a data center. I won't get into a lot of detail here because we've got a limited time, but the options are there. Okay. Anybody got any other questions on what we talked about? We'll take anything on vSphere. We've even got another expert standing by here.
NUMA is a technology offered by VMware. Is that right?
No, non-uniform memory architecture is just, I would call it, it's not fair to say it's an Intel aspect, but like the Xeon processors from Intel kind of were the first to materialize this. Go ahead.
Yeah, I think this is definitely not the VMware technology. This is a hardware technology, both Intel and AMD.
Yeah.
But most of the server has NUMA. In the data center, I'm saying not the personal computer. Personal computer usually don't come with NUMA. But other data center servers mostly are NUMA servers.
Yeah, I think it was an artifact once you went to multiple sockets. Just because of limits with speed of light being close to these CPU sockets and you know, finite bandwidth interconnects, they just couldn't make. I think the designers were ultimately faced with the choice of keeping it uniform, but limiting the number of sockets, or going up in socket count. And
yeah. The reason it has NUMA is trying to have an architecture that can extend. So if you only have one socket, you actually has limits. So you limit your potential to design a computer that how much memory you can have, because your one memory bus or the number of memory bus can only support so many memories. So if you want to design for example, the HPC, the high performance compute,
Like we have the Tianhe. So all those high performance supercomputers, actually they have to be non-uniform memory access, because this is how they have a really powerful supercomputer that has giant memory and CPU and the GPUs and work as one computer.
Yeah, those cores actually have even like L2 and L3 caches sometimes. So, and they're right physically on the silicon chip, moving out to the DRAM strips. And if you tried to get DRAM strips, there's something called buffer electronics. To be accessible to all those cores, you have to up the current flow on those. They consume more power, and it just becomes really difficult to do. So you end up with this non-uniform architecture. And kind of the takeaway here is by using a hypervisor, you can carve up the allocation of these physical limited boundaries intelligently, so you're minimizing the crossovers to these low latency and bandwidth choke points. And fewer bad things can go on at random times.
你这个 built-in 的这个 Kubernetes 是有没有那个 monitoring tools， 就是你们自己开发的这个？
So the question is, in our building Kubernetes on vSphere, on VMware, do we have any monitoring tools? I think so. For built-in solution, we have one on vSphere. We have two options. One is purely open source. We showed here is we have cloud provider. And then you just basically download Kubernetes, upstream Kubernetes, and you build a cluster by yourself. Then with this, you have to continue to build a solution by yourself for monitoring premises and others. But we do offering the enterprise solution we call PKS. And PKS definitely has the tool to
and I guess it depends what you're monitoring. So Kubernetes has monitoring built in or optional. Some of this is optional, but there are CNCF open source projects that are very popular, like Prometheus. And I would contend for the most part, they're geared towards monitoring the software applications that are running. And if you're on a hypervisor on-prem, you might want to get into, if your definition of monitoring includes that a fan failed in a physical server or something like that, vSphere itself has things there that out of the box, you're not likely to find built into Kubernetes. You might be able to route those through to something like Prometheus, but in vSphere, they're generally on a supported hardware platform going to be automatically done at the hypervisor level. Some of these DRS functions, the slides I couldn't get to with high availability, will actually proactively monitor that for you and engage in, let's say you have one power supply fail on a 2 power supply server. You might be able to have this thing give you an early warning, or potentially, depending on your configuration, even allow you to avoid that or evacuate it, so that when somebody comes to take that server down to service it, there's not even the slightest disruption. So I think it's fair to say there's plenty of monitoring built into Kubernetes. There's also external third-party monitoring solutions that a lot of people use. But in addition to that, when you come down to the kind of, let's say, the hardware level, there's still great value in what's available in vSphere. And I think there are drivers that might route that into Kubernetes so that nobody wants to look at 5 panes of glass to keep an eye on this. So ultimately, it's more important that the collection is there. And all of these things have APIs so that if you wanted to, you could cause these to go to some central collection point for ease of consumption. Yeah. Okay, I think we're pretty much at our limit, if not over. But if we didn't get to your question or you want to ask it privately, catch us now before we leave the building. Thanks.
Thank you.
谢谢。